So this is obviously chapter 6. That's why it says chapter 6 right there in like 48 font. Chapter 7 is coming up after chapter 6 and before we go to chapter 8. All right. Some years I give chapter 6 and 7 tests. Some years I give just chapter 6 tests. Depends on how I feel. We'll probably do chapter 6 just so I can get one more score on your grade. You're welcome. It'll be really hard so that people fail right before transfer window opens up. No, I'm just saying. Here we go. It won't be that bad. In fact, one of the free response maths we're going to do actually today. The problem is we won't test for a while. This is one that's just algebra. It's not that bad. So if you're taking notes, like put it in a giant box and say, this is the test question. Like I changed one number, that's it. All right, so this can be a little bit tricky. Next week I'm hoping to have a guy come in. His name is Lee Davis. He's an engineer at ATK. And he does a fantastic presentation on the electronic structure of atoms. He talked about a book that he got most of his information from. So I bought that book and I started reading it and realized it was like 5,000 feet over my head. So it was really good for the first like 28 pages. Then I was done. No. Yeah, well, you're not going to read that book. I should assign it for a book report. All right, here we go. So really, I think the reason I love this is because it's physics, and physics is true. Chemistry is kind of a lie. And what I mean by that is physics is just pretty much based on math, and math usually has a right answer and only one answer, right? But chemistry is not, and sometimes it has an answer that says this, but under different conditions it'll say that. So this is physics. I love physics. It changed my life. I didn't understand math until I took physics, and then I never struggled in math since. So here we go. The first introduction to the electronic structure of the atom, or chapter 6, is an introduction into waves. Waves are simply propagating energy, essentially. All right, so to understand the electronic structure of atoms, one must understand the nature of electromagnetic radiation. Now, electromagnetic radiation looks a little bit different than this pretty wave just right here. It's made out of two different types of waves. Any guesses what they are? The electric part and the magnetic part. So we call that an electromagnetic wave. And I can't draw it very well, but you'd have another wave that would be like this. Like I said, I can't draw it very well, but they would be like 90-degree angled to each other. You all right with that? You know, it doesn't matter, but you need to know what wavelength and amplitude are, and frequency. So first off, wavelength is the difference from the top of one wave to the top of, well, it's one wave, but of one top to the other. And really, it's from any point on the wave to the exact same point on the wave later. Easy enough, right? That's the wavelength. The amplitude is how far it is up or down from the center. It's not too hard. In this class, we hardly care about amplitude at all. We care about wavelength a ton. And this is probably the first time you've seen this, in this class at least. The symbol we use to represent wavelength is called lambda. And it's Greek. I probably spelled it wrong. I don't care. Lambda. Okay. So from now on, if I draw whatever you think that looks like, an upside down Y maybe, I'm talking about the wavelength. Easy enough? Now, wavelength is typically measured in meters, but in this class, we're almost always going to measure it in nanometers. So do you remember looking through your little spectroscopes? And there was a 6, 7, and 8. All right, those 6, well, actually it was 4, 5, 6, 7. Those were tenths, no, those were hundredths of nanometers is what that number was. Yeah. All right, anyway, nanometers is 1 times 10 to the negative 9 meters. Next up. Oh. So the number of waves passing a given point per unit of time is the frequency. For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. And in this class, every wave we talk about is always traveling at the same speed. And you may already know what speed I'm talking about. The speed of light. Does anyone know what the measurement for the speed of light is? Ten to the what? Okay. And that's meters per second. But just a second ago, I said we usually are going to use what? Nanometers. So you should also memorize the speed of light as 3 times 10 to the 17th nanometers per second. And if, I hesitate to say this next hour, but if you're a calculator person, put those two numbers into your calculator. I have had them for years. Well, that's kind of tricky. My calculator batteries died so bad 2 years ago, I lost everything I've had. But I had them all programmed into my calculator for over 20 years. So this would be C and M. If I hit that variable, it would pop in C, which we call the speed of light, and M, that meant it was in nanometers. Because you'll use this number a lot. If you take a physics class, and I don't know how much they do on light over there, you'll use this number over and over and over. But in chemistry, we typically talk about this because when we talk about light, our eyes observe light between 400 and 700 nanometers. So we just kind of stick with nanometers. Because saying what it really is, like 10 to the negative 9 meters, that's a pain in the butt, right? So we just say nanometers. All right, so there's a couple of things right off the bat. All right, all electromagnetic radiation travels at the same velocity. There we go, I should have been more patient. And that's the speed of light. Just a second ago, I blew past frequency like it wasn't even important, right? I better go back there. All right, I'll come back here. That's why we have first hours. So we can screw up and then fix it so second hour is perfect. All right, so my example up here is that this box, it's tricky, but you'll do this a lot when you take a physics class. That box is going to represent a snapshot of time. So it's representing a second. You okay with that? So to find the frequency, we would count how many times the wave travels or how many wavelengths are in this box that we're defining as a second. So you can see it went from here to there. I swear I changed colors. All right. And notice, at this point on the wave, if we were drawing it, we'd be going up that way, right? If we were drawing this wave, we would also be going up there, correct? So it's the same place on the wave. So 1, 2, 3, 4 and a half, right? So we would say that this wave, that as drawn, would have a frequency of 4.5 per second. That looks like a 5, right? All right, now, it's kind of weird to put a denominator without a numerator in the units. But that's what it is. It's also called a hertz. All right, anyone want a hertz donut? Okay. It's the oldest joke in the book, right? If you don't know what it is, here you go. Ask someone if they want a hertz donut, and they say sure. Then you punch them, and then you say it hurts, don't it? There you go. We made that one up in the 70s, I believe. All right. All right. Anyway, so the units for frequency are hertz. And now I'm going to get rid of this for all this for a second. A hertz, Hz, is really, in this class, always written as S to the -1. So it would have been, this answer right here would be 4.5 s to the negative 1. What does negative 1 mean? It means 1 over s. It's putting the second on the bottom. Okay? Now, the units for, the symbol for frequency is, it's not a V, even though it looks exactly like a V. This is called a rho. I didn't get to make it up. Okay? Because we're going to use C to represent a velocity and a V to represent frequency. Yeah. All right. We all right with this so far? All right. So now let's go back to this. And this will tie them all together. So this is kind of nice. Since the speed of light's constant, this is only a two-variable equation, right? C is equal to lambda, and I'm going to call it V, even though it's really rho. You okay with that? No. In real life, like in physics, they say C equals lambda F, which makes sense. An F for frequency, because we're in a different class. Because it's not lambda fluorine. I don't know. I'm just kidding. Yeah. I don't know. The truth is that it's this V. But just remember, V is really talking about F, which is frequency. And this is the more common way. We're going to write this, which is just I don't even know what the right word is. I call it conjugated because it seems to be a good idea, but that's really a language term. But whatever. That's the rearranged version where we solve for wavelength because that's typically what we want in this class. So wavelength equals C over rho, or frequency. Okay? Now, you might notice, and this is not like this is on the exam. Now, this is not the part that I told you is the free response question. We will do the entire free response question later, but this is definitely part of it. So yes, it is this. This is a three-variable equation, so it fits nicely into one of these circles. A review, when you use the circle, you cover up the thing you want, and whatever's left over is the thing or the math that you do to find it. So if you want C, sorry, I just am an idiot. If you want C, it's lambda V, right? If you want frequency, it's C over lambda. Lambda is C over that. I think I already said that, but whatever. Remember how to use that? Okay. This is on the test, and I should put a side note here. And should hopefully be easy. Hopefully. I think there's two free response or multiple choice that are just straight up this problem. All right, now, so hold on. One more time. Waves, let me try and draw a little bit better. Light is an electromagnetic wave. It propagates through space in three dimensions. You have like the wave here, and then you have the wave here. Just trust me for a second. I know what I did wrong last time. And like this one's coming in and out of the board. And what's the red one doing? Yeah, it is. It's just up and down, right? So red's going like this. You can do it. This is fun. See how coordinated you are. So red goes that way, and blue's going that way. Do it. It's hard, but that's what light waves do. They're made out of two separate waves that propagate through space along two different planes. What do we call one of them? The electro part. What do we call the other one? Magnetic. It doesn't matter because it just depends how you looked at it. Are you all smart enough to know that electricity and magnetism are 100% related now? Not from this class, but from before you got in here. It's okay. How do we produce electricity? We spin something in a magnetic field and it produces electricity. Like, what the? It's the weirdest thing on the planet Earth. And all those weird ways that we can think to create energy except for solar, all it does is a different way to spin a thing in a magnetic field. And usually we're just spinning copper. Electricity is the craziest thing that I can literally think of. Why, if I have a magnet and I have a piece of metal and I move them, is all of a sudden current produced? That's messed up. And amazing. Why did I take this over there? Okay, so light can be described as a wave. It is. It's a light wave. But life isn't so simple. All right. Turns out that, and you read this, I hope this is all just like, oh, hey, this makes sense. I kind of read this already. If it doesn't, just flatter me and say it does. It's my birthday Sunday, so be nice to me. Heart. Thank you. All right. The wave nature of light does not explain how an object can glow when its temperature increases, though. So, like, you turn on your stove, all of a sudden your burner starts to glow orange, right? Right there. That just blows everything I just taught you out of the water. That doesn't make any sense. Max Planck explained it by assuming that energy comes in packets called quanta. And we're going to get to this after we have this discussion that I've never had before, and it might be a disaster. Sound good? All right. So before we move past really this idea, I want to talk about a few things. Kylie knew this lecture was coming up, so she wore all black. Good job. So we have this concept of what we call blackbody radiation, which can be pretty tricky. But the idea of blackbody radiation is something that absorbs all light. So this is a diagram of a perfect black body, not you. All right? So inside this box, was that offensive? That's funny, right? Okay. Okay. All right. So inside here, this box is lined with something black, like graphite. And all light is completely absorbed. All right? Just like my short shirt, and really half of you are wearing some version of black today. It's absorbing light, right? All light in a black body radiation is absorbed and not emitted. Unless you heat it. And then all of a sudden it starts to produce light. That doesn't make any sense in the wave-like idea of light, which we call the classical model. And what's even more unique is that it changes colors under certain temperatures. That didn't make sense at all in the classical behavior of light. The classical behavior of light, you can walk out when you need to. This will be on the internet if you are enjoying this. Just look it up from my YouTube list. All right. The classical model of light, this is crooked, that's why, said that as I approached a really, really short frequency, that my energy should become infinite. That doesn't happen. It just straight up doesn't happen. But the wave idea and the C lambda F and then the relationship of E to it, and we'll learn in a minute, says, hey, it has to. If the frequency goes to zero, then the energy or the wavelength, everything should pretty much go to infinity. But it doesn't. The observed values show that the energies of light followed this curve. It was called the Ultraviolet Catastrophe, which is a little bit melodramatic, but whatever. It didn't ruin anyone's lives, I'm pretty sure. All right. It might, though. We'll see. It's still young. It's only a couple hundred years old. All right. So this is what was observed. But this is what should have happened. And anytime in science we observe something that doesn't match our models, well, that ruins the model, right? So that's why they called it the catastrophe. So they had to explain why they were getting results like this instead of results that they thought they would get. And this is where the idea of the quanta or quantization comes. And it comes from Planck, and it comes from Einstein's explanation of what we call the photoelectric effect. Okay, the photoelectric effect, did I put these in the right way? Sure. All right. The photoelectric effect is just like when you microwave your spoon. Who's put metal in a microwave before? You turn it on, and almost immediately you got sparks, and you almost don't even know what to do. You're like, do I call 911? Or do I go to the bathroom? Because that was a weird experience. All right. So you have this piece of metal, and they didn't have microwaves back then, but they could take a piece of metal, and they would put light on it, and they expected, I should say, and I'm hoping this makes sense. They expected that if you put this piece of metal under light and you increase the intensity of the light, that it would start giving off its own light. Okay? Because some people had observed that, hey, you radiate a metal, it will give off light. So they're like, well, let's study this weird thing. So people started to study it, and they were testing the intensity of the light. And it turned out that the intensity of the light had nothing to do with the electron being emitted. It was the wavelength of the light. So you could get the brightest red light ever imagined and put a piece of metal under it, and it won't start to emit its own light. It won't give off sparks, essentially. But you can take one of the dimmest violet lights that you've ever seen in your life, and you put it on the metal, and it immediately would start to emit light. So their hypothesis that it was the intensity of the light causing the thing to emit was wrong. They discovered it was the wavelength of light or color of light they were radiating the metal with. And they found out the electron would only be emitted, that's when it produces light, from the metal under exact wavelengths. And it wouldn't do anything until you met that wavelength. And then it would like continue to give off light, and then you hit a different wavelength, and then it started to give off light in a different color. So they explain the photoelectric effect with this idea of quantization. So here are some of the nuggets, by the way, of the photoelectric effect. The electrons were emitted immediately with no time lag. And let me try to put that craziness into your mind. It's kind of like they were trying to light a fire. And with certain matches, nothing would happen, but with some matches, it immediately went. Like your fire went from nothing to full fire, like that. Okay, yeah, so they poured gasoline, and it went. You okay with that? And it wasn't like how long they heated it and it finally got hot enough and then it lit on fire. It was that it immediately went. All right, next. Number 2, increasing the intensity of the light increased the number of photoelectrons, but not their maximum kinetic energy. So they found out that intensity will help with how many electrons are ejected from the metal, but not the energy of the electrons. I can sort of explain that by talking about a waterfall. Waterfalls work in physics quite a bit, and they work in chemistry once in a while. The energy of the water that falls over is strictly dependent on how far it falls, right? Not how much of the water is falling. So if we're talking an individual water particle, its potential to kinetic only is dependent on how far it falls, not how many of them are falling. It's the same idea here. All right, number 3, red light will not cause ejection of electrons, no matter what the intensity. I already kind of said that. And then 4, a weak violet light will eject only a few electrons, but their maximum kinetic energies are greater than those for intense light of longer wavelengths. All right? The explanation of the photoelectric effect came from a guy named Albert Einstein, and it's what he won the Nobel Prize for. And you can see it says the explanation marked one of the major steps towards quantum theory. Quantum theory is what this whole chapter is about. And quantum theory is like one of the craziest things that you've ever learned, and it 100% supports the structure of the periodic table, which was arranged way before they were able to prove quantum theory correctly. It's pretty amazing. All right, there's a tiny bit more. So I'll just kind of read this. You can read it too. Analysis of data from the photoelectric experiment showed that the energy of the ejected electrons was proportional to the frequency of the illuminating light. This showed that whatever was knocking the electrons out had an energy proportional to light frequency. The remarkable fact that the electron energy was independent of the total energy of illumination showed that the interaction must be like that of a particle, which gave all of its energy to the electron. The key word there is that it's like a particle, not like a wave. All right? This fit in well with Planck's hypothesis that light is the in the blackbody radiation experiment could only exist in discrete bundles with energy. And he comes up with this equation right here. This equation is extremely important in this class. We write it slightly differently. We have, I'll write it up here, H, and this is the rho, right? HB, whatever. All right? We take this equation, and we take the equation that we just barely had, and we combine them. So the equation we just had said that we had C equals lambda and rho, right? So what is rho equal to then? Whoops, I wrote lambda. Thank you. That's why you're looking at me funny. You're right. There you go. What's that equal to? C over lambda, right? Algebra says if this is there, but it's equal to something, I can substitute, right? So really, I could say the energy is equal to this new letter, H, and then what this was equal to, C over lambda. And that's the equation we will use the majority of time in this class. It's the equation that can relate the energy of light to its wavelength. H, we're going to learn in a minute. That is Planck's constant. I think it's 6.64 times 10 to the negative 34th. That'll be on a slide in case I'm wrong. E is the energy. It's what we solved for. All right, I'm almost ready to tie this all up and explain why this has anything to do with your microwaving a spoon. All right, so what this picture is showing was their experiments. They have red light becoming incident to the plane of the metal, and red light did nothing. They take green light, and it ejects an electron. This is its velocity, which we don't necessarily care about, but it was able to eject an electron with a certain energy. And then purple comes in and it ejects electron with a different energy. Notice that this one has a higher velocity or a higher energy. You okay with that? Green was lower. All right. Most commonly observed phenomena with light can be explained by waves, but the photoelectric effect suggests a particle nature for light. So what they're now saying, who's ever played pool? You ever hit a pool ball and it hits another one and the one you hit stops, but the other one goes? Okay. That is the explanation of the photoelectric effect, sort of. This comes in and it's not a big enough pool ball to move anything. This one is, but it doesn't move it very fast. This one is and kicks it out really fast. It's a complete transfer of energy, like two balls colliding and one staying and the other one going. All right? Now, so real quick, I have a picture right here, right there. So I don't know what piece of metal this is in a microwave. Doesn't even matter. But think about your spoon. Your spoon's sitting in here and you're like, I don't know, your oatmeal. And it's just hanging out. It's made out of a metal, which means there are electrons on the outside that are free to do what they feel like. In your microwave, a certain type of electromagnetic radiation comes in and hits your spoon. Do you know what that's called? A microwave. Nice. So a microwave hits it, and a microwave has a lot of energy. That microwave hits your electron, and it jumps. Now, it doesn't leave the spoon. This is not drawn to scale. But it jumps farther away from its nucleus. It doesn't like to be away from its nucleus. So what happens? It has to come back down. And as it comes back down, it gives off its energy. I pointed that way. It gives off energy in the form of light, or the sparks that you see. You all right with that? It's the same idea as the photoelectric effect. We're just using a microwave instead of visible light. Now, the analogy that I like to tie this to, you'll remember if you had me last year, is when you played crack the egg on a trampoline. I don't want to waste my time. So on a trampoline, they picked some girl this year that was super small, but I can't remember her name. You have like a really small person that you're going to play crack the egg with. All right, so who's the smallest person in this school? Something Jex? Your little sister? Okay, she's pretty tiny. I've seen her. So she's going to play a game of crack the egg. Who's played crack the egg on a trampoline before? Okay, so it's essentially a game of chicken where it's either break my neck or stay cool. Right? And we are all walking, so we all chose to bail out. We're not going to be cool, but I don't want to break my neck. All right, her name's Lizzie. Lizzie. I-E. All right. All right, so she's going to play a game of crack the egg with Tyson Madsen. Do we know Tyson Madsen? He's like 6-something and 300 pounds. 300 pounds. I get to do driver's ed with him on Saturday. I'll probably sit next to him and get elbowed by him at the same time while he's driving. I don't want to. All right. Oh, we are not talking a perfect black body, right? All right. So here we go. So in crack the egg, the goal is to make this person pretty much almost die, right? Yeah. So Tyson's going to go up and down, and he's going to gain energy, right? And then he's going to land, and he's going to do that all trick that all of us on trampolines know, where you like buckle your knees or whatever, and you take all your energy, and you do what? You give it to Lizzie. All right? And then Lizzie, she's thinking, I got this. I'll be fine. Oh, hey. Whatever. Okay, so just imagine the trampoline didn't go with her. Yeah. All right. So she jumps up, or she flies up, right? But she has to come back down, right? Tyson's big, but not big enough to bounce her into orbit. I'm pretty sure. All right. So as she went up, she's holding on. Going up on the trampoline isn't the scary part. Coming down. So now she starts to come back down. She's going to let go of her feet, first off, because she knows she's about to die. Okay? Lets go of her feet. Starts to do that, like kick your legs, wiggle your arms to try and get your equilibrium back. But at the same time, she's also going to start screaming. You okay with that? She's going to give off a sound wave. You sort of with me? Who's with me, sort of? All right. Now, maybe she doesn't really scream, but this... Okay, she would. We have data. All right. So in a very weird way, we took Tyson Madsen's energy and we converted it into a wave. You with me? And the wave came from something that wasn't Tyson. Who's with me? Okay, so Tyson's representing the microwave. What's Lizzie representing? The electron. And what's the scream representing? The light. And the higher she bounces, probably the higher pitch the scream. Probably not how loud it is. But let's say my 4-year-old daughter gets on here and does this. Is she going to make her scream? No. She might laugh. Like, good luck. All right? My son's 13. Probably not. You have to get to a certain level before you can get that out. That's the idea of the photoelectric effect and trampolines. All right. Blue sheep, leave them there. Hey.